All right, so we've got here particle is located at a position vector with respect to an axis of rotation, and they tell you that the definition of torque is this R F sine alpha,
Yeah.
and the idea is that you whatever you're taking your torque about, there's a distance r away that a force is generally being applied to it.
Okay.
And the alpha is this angle between the two of them. Now I have no idea what this question actually wants. It says a torque is applied about axis A due to the force F. A picture would really be helpful here. Maybe there is one down below. Yeah, there is. Okay. So let's see. Torque A by the force F. Okay. I don't want to give you the wrong answer, but I want to say that it could be that it's just zero because it's at the origin there. It's at the place where you're taking the torque about.
Okay.
But let me check. I mean, this is
That
just
is
a
correct.
standard. It's correct. Okay. I still have to sort of check here because the rest of these. So part B is asking, what is the torque B about axis B due to the force F? B is located at point 0, comma B. Okay, so it is. Okay, so I guess it says due to force F. Yeah.
Mm-hmm.
Okay, let me snip that picture, and that will be very helpful. Well, okay. All right, so we want to know about F here, about point B. So F has a component in this direction. This is F cosine theta.
Okay.
And it has a component in this direction, which is really over here, by the way, which is F sine theta. And if it goes through, if the force goes through that point, there's no torque from it. But this one that's perpendicular to it does have a torque. Okay, so the question in part B is asking for the torque about
B.
Yeah, B due to force F. So it's just this F cosine theta, and then you need this distance here, which is B. So it's B times RF. It's force times distance, but R is B in this case.
Mm-hmm.
Actually, they use lowercase b. It looks like. Oh, that's weird because it's uppercase B in the picture. But okay, yeah. So it's just lowercase b times F cosine theta.
Oh, okay. So that's how you set it up. Theta. That's correct. What's the torque of TC due to about axis C due to F?
So I got to copy this picture again. So we're now interested in the torque here.
Is that the CA point? That little gap?
This point here. So again, this force F is broken up into two parts. It's got this part that goes right through it, and then this part that does not. The
Mm-hmm.
part that goes up here is F sine theta.
Yeah.
This is F cosine theta. If it goes through there, it has no torque. But this F sine theta, it's a distance of C away. So the torque is R times F. The torque is the distance C times F sine theta.
Oh, so it's just a cross. Okay.
It's just this vertical one, and it's a distance of some amount away.
Wait, so keep in mind that the force is applied at axis A, not at axis C. Will this produce a counterclockwise positive or clockwise negative torque about the c-axis?
Okay, so that means it's negative because there's direction to consider, which is like part of this.
Yeah, that's correct. Negative.
Okay.
What's the torque about D due to F? Now we're interested in that one.
Distance D from the origin. Okay.
Is that going to be sine again or no?
Well, it would be ideal if we knew where this point was, and we kind of do. So this point right here it's a distance little d. Actually, I probably should recopy the picture. That would be probably better. So this right here, it's a distance. This length here is d. So this is d sine phi right there, that distance. And then this distance up here, which is the same thing as the one down here, is d cosine phi. This is all symbolic, and that's why it's kind of a pain in the butt to do. So this force F, as we've done in all these problems here, it has a component this way, F cosine theta, and it's a distance d sine theta away. So your torque is R times F. In this case, your distance away is d sine phi, and then the force is F cosine theta. That's one of them. And then there's this other part of the force, which is in this direction. That's F sine theta. It is a distance because you can actually slide this vector up here, and then it's a distance d cosine phi away. So it's d cosine phi, and then F sine theta away. Now, from the previous problem, we have to determine whether, which way is positive or negative. So they tell you that the torque going this direction is positive, and there's this thing called the right-hand rule. Have you heard of that in class? Maybe right-hand rule.
I think so.
Okay. Well, this one along here, the one along the x-axis, it kind of swings around this way, this torque.
Okay.
So this one is positive. This one swings around the other way, so it's negative. So it's
right is negative, right?
It's not right. It's a rotation. It's like spinning a
Clockwise.
bottle.
Oh,
Like
okay.
when you tighten it, depending on which way you go. This is one of the really hard limitations of what we're doing. It depends on the way that your hand curls when you're rotating something. Whether and they chose arbitrarily that's that and that. We'll do another problem where this is more clear. This one isn't. So the answer is it's all of this minus all of this.
Oh, all right. What are you left with then?
I'm not sure what you mean. It's all of this.
Oh, it's all of that? Oh.
Yeah.
So I add both those together? Is that what I do?
Well, one's positive, one's negative. So this comes up here to go with it.
Okay, I see.
D sine phi F cosine theta minus D cosine phi F sine theta.
Okay, I see what you mean. I thought that there was some simplifying involved, and I was obviously wrong there.
Nope, nothing more for that one.
F cosine theta is right here. Minus D cosine phi F sine theta. And that's correct.
All right, so the next question I see is about the end of a song. It says it's 6 of 17.
Yes.
All right, so we got a CD rotating here. Let me snip this question. Okay. CD rotates clockwise at 500 revolutions per minute and then spins down to 0 in 2.6 seconds with constant angular acceleration. What is alpha, the magnitude of acceleration as it stops? So there's a formula here. It's like omega final minus omega initial equals 2 alpha t.
Okay.
Does that seem right?
That does seem right to me.
Okay, I gotta confirm that here, but it in the direction that's spinning doesn't matter at all. So the because it could go either way. So the no, it's not 2 alpha. It's just alpha t, I guess.
I see.
So that's no good. Okay, the initial I'm sorry, the initial is 500 RPMs. Omega 0 is 500 revolutions per minute, but you're supposed to know, oh, that's the wrong units here. So in 1 minute, there are 60 seconds, and 1 revolution is 2 pi radians. So this gets us down to the units of radians per second. So whatever that is, but you can just keep it as 500 times 2 pi over 60. That's omega 0. Omega final, that's 0 because it says it's 0, like it stops. And then we know the time is 2.6. So alpha is equal to omega final minus omega initial over t. Omega final is 0. Omega initial is this expression up here, 500 times 2 pi over 60, all over 2.6. And if you got your calculator handy, see what you get for that.
Yeah, I'll get that out.
The thing that's sort of bothersome here to me is that so alpha, it is negative, but it just wants the magnitude, which means that you're really finding the absolute value of alpha.
Let's see. Divided by 60, 52, divided by 2.6. Negative 20.13.
Yeah, and like I mentioned, you have to take the absolute value of that number because it only wants the magnitude. So it's 20.14. That's probably too many. It's probably 3, so maybe you go 20.1 radians per second.
That's correct.
For that.
How many revolutions does the CD make as it spins to a stop?
Number of revolutions. Okay, so we have this is going to be something like theta final. Number of revolutions here. Let's see, theta. Slowing down. We have alpha now. It seems like we can go theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. We have these numbers. Omega initial is 500 times 2 pi over 60. We know that time is 2.6 plus 1/2, and then we use that unreduced number over here that we got for alpha times 2.6 squared.
Is it alpha 2.6 squared?
Well, all of this is alpha, but you have to you should know by now that you can't use the unreduced version. You have to use the non-reduced version. Like you have to go out to a bunch of decimal places to find it. So yeah, it was 20.14, but you really want to go with the much larger expression. So 500 times 2 pi divided by 60 times 2.6 plus 1/2 that alpha value you just found times, and I get here 204 radians, which may or what does it want your answer in?
Here, express them in sig figs and revolutions.
Okay, so that's radians, and then 1 radian is 2 pi.
Okay, so 204.
No, I'm sorry. There's 2 pi radians in 1 revolution. So it's that answer that you just got divided by 2 pi. I don't know. I might need the full wording so I can search for it if this isn't
I
right.
get 320.
I get 32.5 here. Remember, when you divide it, put that in parentheses.
Oh yeah. That is incorrect. When I got my answer, I got negative 324 for the top because of that 502 pi divided by 60 times 2.6. Oh wait, no, okay, I see what I did wrong there.
Oh, and well, ooh, you know what? I have the wrong alpha because I didn't put a negative in.
Oh, I get 596.
Yeah, I need the full wording here. I'm not gonna be able to help you with this part. If you want to send over a screenshot, I can look it up.
Get those going.
I'll try searching here, but it's often you need Google needs the complete wording here. Let's see if this one actually might be okay. So the part B. All right, so this one is actually we actually went down completely the wrong road. Maybe it'll give us the same answer. So it says here that there's this other formula which is omega final squared minus omega initial squared equals 2 alpha theta. Oops, 2 alpha theta. We have all of this information. We know that the omega initial is the minus 500 times 2 pi over 60, all of that squared. We know that omega final is squared because or 0 because it's not moving. Alpha is the alpha we just found, and then the theta is what we're trying to find here. So the shortcut here is you take that number we got from part A, which is let's see, it was like minus 20.138414. So that's your alpha. Take that, and that goes in here. But we're going to use this expression. It's negative 500 times 2 pi over 60 squared over 2 times your alpha value, and that does give you theta.
Oh, I see. All right.
So go ahead and try entering that in your calculator. That actually does seem like it'll work.
Square that up. Divide by 2 alpha. What's 2 alpha again? The number that we get from,
Yeah, from the previous part here.
which is negative, all right, so negative 70.138414. I get 39.1. How do I, what? Dang it, it's not correct.
We get about 68 revolutions. I'm sorry, 68 radians, and then we got to convert that to revolutions. So the number you get here is in radians, and we know that there are 2 pi radians in 1 revolution. So you have to take the answer you just got and divide it by 2 pi. So it ends up giving you about 10.8 revolutions.
Yeah, I get 10.8 too.
So there's this question 7 of 17. I'm missing the picture in the lower left. Let me see if the next one has it. Yeah, that full picture is needed to be able to rank them. If you want to resend that one over, we can do that problem.
Which one is it? Number
7 of
7?
17. It says torque magnitude ranking task.
I see it.
The picture in the lower left there is cut off on the.
Sending it right now. Through the reply. Come on. Attaching that. Down here. That's it.
Okay, there it is. Okay, so the forces are center on the. Okay, there we go. All right. So. All right, so I'm snipping this in, and we'll take a look at it. So the axis here is right along this line here of the wrench. So the first thing is that C is right along there, and that means that the torque produced by C is equal to 0 because it goes along the direction here of this object. Okay, so I think it asks you to rank them from smallest to largest, largest to smallest. Well, that's the smallest. So that's the one that goes all the way on the right. All right. Now, D. Is this the magnitude? Yeah, the magnitude. Okay.
So C goes all the way on the left. Is that what you said?
C is the smallest. It's 0. Okay, so the torque produced by D is all of these have the same, well, B, E, and D all appear to have the same magnitude, like they're the same length arrow. So the torque is always it's the force times distance. Your book goes R times F. So if they're all the same, then what it comes down to is, well, which is the bigger R, meaning which is the bigger distance between the points. You can see that D has the largest distance from that point. So the torque about D is the largest. Okay, so now we have to consider the torque at B and the torque at E. The torque at B and E, they're the same distance away. They're the same magnitude. The arrows are the same size. One causes a torque that direction. One causes a torque in the other direction. The net result, though, is that they are exactly the same. They're just in different directions. This is just asking about the magnitude. And since they're they're the next furthest away, these are the next largest, but they are the same. And the way I think you do that here is you would show like a letter D with an E overlap on it, I think is something how it does it. So that's the next largest there.
D and E are fighting for the largest.
No, they're the next largest. You have you have D already as the largest.
Oh, D is largest. Okay, sure. All right.
Okay, so now we're down to F and E, F and A. F and A. So now, like if you break F up, it's got a component this way and a component this way. You know, one sort of perpendicular and one that's parallel. The parallel one doesn't contribute. Okay, now we can do the same thing with A. It's got kind of a perpendicular and a parallel. It looks to me like F has a larger force that's perpendicular compared to A. If
Okay.
I'm just doing the arrows. So that means, and because they're the same distance apart here. So since F has a larger magnitude, it's going to be here. A has a smaller magnitude, it's there, and then C looks like it's there.
Where's B belong?
B I'm sorry, B and E are the ones that overlap.
Okay. B and E overlap, and then FAC. Right. There we go. And that is correct. On to the next problem.
All right, let me get back to the questions you sent over. Okay, so I'm up to twirling a baton. Twirling a baton. Okay, so this one's like, it's like they, I hate when they give you information on the left and then the right, and then maybe there's a picture. So
yeah, they're not very clear with it.
So we can get this in here. Okay. All right. So the question they ask here, which I didn't kind of snip, is what is the magnitude of its angular momentum about a point where the axis of rotation intersects the center of the baton? Okay. So the baton is a uniform rod of mass, whatever, length 80, and it's spinning through its center. So there's like a baton here, and it's spinning. I don't know, it's spinning. Okay, and it's asking for the angular momentum, so we have to find that value. So that the angular momentum depends on the geometry, and that's why it tells you it's a uniform rod of mass. That way you can get that equation for it. So one of the things that I think would be good to do is, identify kind of the quantities you're given. The mass is 0.12. The length here of the rod is 0.8 meters, and omega initial is 3 radians per second. And then we can see, then you can kind of get a feel, okay, well, what do I need to find, or what formulas do I have that even help here? I don't even know where we're supposed to go on this, because there's some equations for energy, there's some equations for other stuff. So the angular momentum formula is I times W.
Okay.
And for a rod, I is equal to ml squared over 12.
Correct.
You have the mass, you have the length, and 12 is that. Do you know W? Yeah, it's right there. Now, what I'm not seeing here, but we want of the rod about axis passing through something else. Let me look at the picture again. It's not this simple. I mean, it should be, but it's there's more to it here. Where is the picture again? Okay, so maybe that's part B. About a point where the axis of rotation intersects the center of the baton. Not sure. Let's find another reference here and see if we can find it here. Okay, so this one does just do it the way we have here. So let's just go with this. So you have your mass, that's 0.12. you have your L, which is 0.8 meters, and you have your over 12, and then you have your 3 radians for W. Let's see if that works. Let me multiply that. 0.12 times 0.8 times 3 divided by 12. Is it 0.08? Yeah.
Yep. 0.08. Oh.
0.12, 3 radians per second. 0.12 times 80. Oh, it's L squared. I'm not squaring that. That's squared. Okay. That makes a difference. Okay, I get 0.0192. So give that a try there.
Wait, 0.08 or just 0.8?
I got 0.0192. 0.8 is squared because it's L. 0.12 is the mass. 3 is the value for W.
That's correct.
Okay. You probably have to send over a picture of part B. I'm not. Does it say, what does it say for part B?
You're probably going to want to see it.
Okay.
Sure, sent.
Okay. I'll stand by for that. With a skillful move, the major changes the rotation of her baton, passing through its end. Was the magnitude? Okay, so the magnitude at the end of the rod is different than at the middle, which is what we did in this previous problem. I saw the solution, and I guess the maybe the so they say you have to use what's called the parallel axis theorem. Maybe that's something you saw in class. Parallel axis theorem. So now this rod, you're doing it now here at point P, and so there's a bit more to it. The angle, the inertia there is the initial inertia plus ml squared. But well, the book uses h squared, and this h here is right in the middle. H is L over 2. So your I0 is just like we had in the previous problem. It's ml squared over 12, but the one here is m. Since h is L over 2, it becomes L over 2 squared, and you get ml squared over 12 plus ml squared over 4. If you add these up, you end up getting ml squared over 3, and then your L, which is what you're trying to find. Your L is I P times W. That's what you just found here, ml squared over 3 times W. So it's your mass again, your 0.192. Is that what we got?
Yeah.
Okay, so 0.192. The L, which is 0.8 squared over 3 times 3. All right, so I get about 0.123 for this. No, the mass is not right. That's not point. It's 0.12, not 0.192. So that is 0.12. That changes your answer. So it's 0.0768 for that.
0.768. All right. That's correct.
All right. I'm just gonna try to jump back to.
You want to go to one of the problems that's just one problem?
It's up to you. I'm just going through them in order. The next one here is does have just a part A. This is 9 out of 17.
All right.
Is that right?
There.
I mean, I know these are all related, but they don't seem very related for learning. It seems like they're just all over the place.
Is there? Yeah. That's how I feel about it. It's not very structured, in my opinion.
Yeah. Well, if you take some technical stuff in college, you'll see all this again. Which I mean,
I know for sure that I'll take it for what you call it for college. Yeah, I'll take physics in college.
So this one here, what is the steady state? Okay. 35 RPM and 7 minutes. Okay. The moment of inertia equation, which I mean, how do you even know this? No, there's a figure. Does the figure have the picture in it? Have the does it have any equations in there?
This one doesn't have any equations. It's just a circle with a radius on it, and it just says end view of cylindrical satellite. Yeah, there's nothing really useful there.
Trying to figure out how you're supposed to do this. So the torque, I generally work backwards. The torque here is R times F, which equals I times alpha. And let's see, you can calculate alpha. Alpha is omega final minus omega initial over T. We saw that from an earlier problem here. They tell you that it reaches 35 revolutions per minute in a certain amount of time. So we can get that. So let's do that first. So omega final is 35 revolutions per minute, but we know that there are 2 pi revolutions in 1 radian. This is revolutions per minute. 1 revolution is 1 radian, and that in 1 minute there are 60 seconds. Okay, so the value. Wait, why do I have this wrong? This is not right. 1 revolution is 2 pi radians. Like that doesn't work like that's 2 pi radians. Sorry. So that's your omega final, which is 35 times 2 pi over 60. Then your omega initial is 0 because you're not moving, and it tells you that your t is 7 minutes. Well, that's times 60 gives it to you in seconds. So alpha, we need alpha to get this thing because you're trying to find the force, and your force is I alpha over R. So from this first equation. Okay, so alpha is 35 times 2 pi over 60 minus 0 all over 420 seconds. So that's a number. That's alpha. We got that. Great. So now we need the I, and this is where I have no idea how they come up with this. So this is it has to do with the cylindrical shape, I'm sure, flat cylindrical, but it kind of bothersome here. It's 1/2 big M r squared plus 4 little m r squared. Big
Okay.
M is the mass of the big thing,
Yeah.
which is, so big M here is, in your problem, is 4,500.
Yes.
And little r, or I'm sorry, the radius here, I guess it's 4. Yeah, so it's 4 squared plus 4. Little m is 250, and it's 4 squared again. So that's some number. That's some number for I. So we're going to get that number here. So you get 52,000 for I.
Yep. Same for me. What
Okay,
are the
so
value units for this?
well, it's
That's not
newtons,
it?
but that's not the answer. I mean, we're piecing this together. We found alpha, we found I, we're trying to find F. So F is equal to I alpha over R. We finally have enough numbers to do this. 52,000 over, I'm sorry, times whatever that is for alpha, which we'll get. That number goes there, over 4. So I'm going to undo the calculus.
For alpha, I got like 0.0087. Is that reasonable?
Alpha should be about, yeah, it's going to be pretty small because you're dividing by, it's 0.0087. Yep. So
I
it's
get 113 here.
50,000 times alpha divided by 4. Yeah, 113 newtons.
It says it's incorrect for some reason.
Okay, well, let's see. Yeah, don't know. I'll look at another reference here. I'll see if this one is any different. So they do the 2 pi thing. They do that. They do m r squared. That one's not very useful. We just looked at that. 2 pi over 60. Net torque for F equals, they do 1/2 mr squared plus 4 times mr squared. I mean, it could be a units. It could be a, 2 significant figures. So that means it'd be like 110 newtons. That might be everything that's needed there. Don't.
100 and what newtons?
110.
110.
That's 2 significant figures.
110 isn't correct.
All right, well, I don't know. I've got 2 references here that show this is reasonable, although our number is kind of large. Just check the calculations again. 5200 times alpha minus 3.0. Yeah, that's what they're getting. 52,000 is 1/2 mr squared. 4 times that times that. Okay, the I is reasonable. Alpha. They do times R. That doesn't seem right. I don't know. How much more time do you have to spend on this question? I mean, we can definitely figure it out, but
it's fine. Let's just switch to an easy one.
Well, none of these are easy at this point. So they're all going to be like this, where there's multiple steps to get through them. 8.52 is probably not too bad. We'll probably finish that here in the next 3 minutes because it's asking about kinetic energy. And kinetic energy is based on there's rotational energy in this case. You have to know something about the fact that it's a bowling ball, and it's that gives you the equation for inertia that you need for this. So all right, let's see what we got here. So the kinetic energy is, I don't like this form, this one. So the kinetic energy is 1/2 mv squared plus 1/2 I w squared. And the mass is given, the velocity is given, I is not given. Okay, but W is equal to V over R, which makes this a lot better. So it's 1/2 mv squared plus 1/2 I v over R squared. So that becomes 1/2 mv squared plus 1/2 I. I is 2/5 mr squared for a ball. So it's 1/2 times 2/5 mr squared times v squared over r squared. So the r squared just cancel. And you get 1/5 plus 1/2. So it ends up being 7/10 mv squared. That's 7/10. Your mass is 7.29 and your velocity is 3.5 squared. So whatever that is in your units are going to be in joules. Let's get that number for you. 7/10 times 7.29. Interestingly, the radius of the ball doesn't matter. I don't really understand that, but that is what it is. So this is 62.5 joules.
65 joules. Let me try that.
62.5 joules, yeah.
Putting it in right now. 62.5. Okay. That's correct. Thank you, Matthew.
We're stop here. We'll pick back up a couple hours. Thanks a lot.
Appreciate it. Bye-bye.
Bye now.